Good morning, everybody. In my last lecture, I had talked of deposition of thin films from alkoxide systems. I had talked of dip coating, spin coat, screen print, amongst other methods of coating. One of the problems of alkoxide materials is when we have a single component system, let's say it is very easy to get SiO2 gel from TEOS. But as I had stated during powder preparation process during my earlier lecture, if I wish to get, let's say, 2Al2O3 SiO2 gel, what I would have to start off with is tetraethyl orthosilicate plus aluminium, say, isopropoxide. That is, I have to take these two components in molar ratio 2:1 because I have written here 2Al2O3 SiO2 and then go through the refluxing processes which I had described during powder synthesis. If you remember, therein I had stated that the hydrolysis rates of TEOS and aluminum IPR, they have to match. That is the rate at which the tetraethyl orthosilicate and the aluminum isopropoxide will hydrolyze, they have to be equal. Otherwise, what we will have is not the compound what we want. Let us presume for a particular media where I am using ethanol, water media, the hydrolysis rate of TEOS is distinctly different from aluminum isopropoxide. During my earlier lecture on powder synthesis, I had talked of how these are overcome. That is, we either change isopropoxide to a butoxide so that the hydrolysis rate changes, or we change the media. Now, since all of that has been in my lecture in the past, I will not dwell on it. It is a full powder synthesis lecture I had given. So, the number of cases in which we can use alkoxide based methods for dip coating, spin coating, screen printing, these are limited. Limited by the fact that if it is a 2-component system, 3-component system, getting matched hydrolysis rate becomes very tough. Yes, it is true that the lens that the fiberglass lens I am wearing has got a silica coating, but then it is simply from TEOS. And as I said last day, it can be made by dip coat or by spin coat. So, if alkoxide method, in spite of its huge potential, that is, what are the potentials of the alkoxide? It forms a polymeric material, it decomposes cleanly to give us the basic ceramic. We have got all of that, and as a result we can generate very ultra thin, I will not talk of nanometer range now, but definitely ultra thin 200, 300 nm coatings with RMS surface roughness of 2 nanometers or so, means a very smooth ultra thin coating. Alkoxide process is unbeatable. But what about the cases where we require thin coatings from systems which are multi-component? We require dense coatings like the alkoxide based coating method, but their problem is they are multi-component and we do not have matched hydrolysis rate. So, in today's lecture, what I will start off is way of thin film ceramics. Now, everyone has his her own idiosyncrasies. What are thin films? What are thick films? What are ultra thin films? The physicists have a basic thumb rule, is if a film is thicker than say 1 or 2 microns, it is a thick film. Any film which is greater than say 2 microns or 1 micron, depending on whom we are talking to. Thin film is less than 1 micrometer, and less means what will be the ballpark over here. The ballpark over here, I would in my own way is I go down to 0.2 nanometer. This is a my zone of thin film, which is basically what physicists talk of. And ultra thin is less than sorry. This is 200 nm. I'm sorry, I made a mistake here. Anything less than 200 nm is ultra thin film. To give you a rough idea, let me put it this way: an average lattice size of any compound is in the range of 3 angstroms to 5 angstroms, maybe larger, smaller. So, in this 200 nanometer thin film, how many lattices will come in? You divide this by the lattice size and you get it. And hence you know what is ultra thin, how many unit cells under ideal conditions, if we pack, they can stay together. In some cases, ultra thin is anything below 100 nanometers also. So, let us say this is thick film, anything greater than 1 meter. Thin film is in this range, and ultra thin depending on where you are. Now, let us look at, let us do some hand waving and let us see what is the best way of having a thin coating. All of you have seen paints being applied to the walls. They apply a paint with a brush and they apply to the walls. Those are thick film coatings. The simplest place where you have seen at home thin film fabrication is, for example, soap bubbles. Soap bubbles are in the thin film zone. Another place where you get thin films is if water is boiling, you put your hand on top of it, moisture, the water evaporates, and slowly the moisture comes and collects on your hand, and your hand is coated with a thin layer of water. So basically, the fundamental process of going from solution to a thin film would obviously be that I have to take the solution and I have to process it in such a way so that the solute gets deposited on the substrate. Now, let me take a very simple case. Let's say I want a thin film of zinc oxide. Zinc oxide is used in many places. I have chosen it simply because it can be done at a lower temperature. But it could be, for all I care, titanium dioxide also, a much higher melting compound. Zinc oxide sublimes. Now, I have given you a project where I have given you a zinc salt, water, and I have said you have got all the facilities in the laboratory. I want you to deposit, say, 1 micrometer thick, dense, uniform, means low RMS zinc oxide film. How would I go about it? I would choose a compound like, say, which is available in the laboratory, zinc nitrate, zinc acetate, any of these salts. Dissolve in water. If you ask me what is the concentration, should it be 1 molar? Should it be 0.5 molar? Should it be 0.1 molar? Should it be 0.01 molar? Let me not answer this question now. Let me answer which concentration would I choose after I have described the experiment. So, let us say we have taken an X molar, you can make your pick, zinc nitrate, zinc acetate. Now, in the laboratory, let me say you do have Pyrex tubes which can withstand temperatures of up to, say, 500 degrees centigrade. Better still, if you have got quartz tubes which can withstand temperature up to 1600 degrees centigrade. Second, you have got in any laboratory today, you have got heaters which look like tapes, tape heaters. They look like tapes which has got resistively loaded coils in it. Outside cover is insulating cloth. These are the two leads. This tape heater can be, say, wound around, say, any subject like this. These are the tape heaters. These are the tapes. You can wind it around it. So, This is normally available in the laboratory. Any of these salts are available in the laboratory. A tube Pyrex quartz would be better. Say a 3-inch dia tube. What I would do is, I would take this Pyrex or the quartz tube, it would be about say 30 centimeters long. At the diameter, I would put at say 7.5 centimeters. The resistive heater, which I call the tape cloth, would be placed somewhere around here. So, this is the area I will be able to heat by this resistive heater. Now, next thing is the substrate. On what material do I want to deposit it? So, here is the substrate which is held, and this is a shaft connecting the substrate which rotates it. Why is this required? This is the substrate, this is the shaft which rotates. Now, this rotation is not at 1400 or the motor speed. Here I want slow rotation, say 5 to 10 RPM would be very good. So, this shaft rotates at 5 or 10 RPM, at the same time rotating this substrate. Now, as I said, I will take a salt. So, what would I do? I would put a nebulizer. A tough term, eh? Well, a nebulizer is nothing. If you have in hospital, you have chest cold, you are choking, what they would do is force air into your nostrils in the form of a fine, very fine jet spray. So, this nebulizer has water as air carrying a very fine mist of solution. Now, in this case, the solution is either zinc nitrate or zinc acetate. Let me take zinc acetate as a salt which was used. So, this nebulizer is connected to a flask which has say zinc acetate solution, and I won't draw the details of this whole diagram. It has got a very ultra fine nozzle at the top. For those of you who use Colleen or any of those things for cleaning windows, what you see is there is a small jet at the front. You squeeze the handle, very fine jet of the cleaning liquid comes out, and that is all that is over here. The head of a Colleen liquid bottle, which is used for cleaning glasses and all those things, is no different from the head over here. This can be made of glass, this vessel can be made of glass, or this can be made of polymer. Now, I've got the zinc acetate solution over here, and I have now connected this part to a compressor. The compressor pushes the water down up through the tube, and here it forms a very, very fine mist. What happens to the mist? This mist will travel up. As this mist travels up, the zinc acetate breaks down in presence of air or oxygen to give you zinc oxide. And this zinc oxide deposits here. Now here on this particular substrate surface, if you look at it, if I draw the substrate subsurface in a very magnified scale, this is this substrate surface. So as you are applying pressure to this nebulizer, the nebulizer emits a spray of zinc acetate solution which gets into this hot zone, and we know at what temperature does zinc acetate decompose to give you zinc oxide. The reason why I picked up zinc acetate was zinc acetate burns very cleanly. It does not leave behind a carbon residue. So here, this zinc acetate mist will travel through this hot zone up and hit this surface. With time, first we may have a few random deposits depending on the nucleation area. Then as more zinc oxide evaporates, they keep building up thicker and thicker layers, and this layer I have drawn only two monolayers. Now remember, this is not a thick layer, this is a monolayer. So more layers of zinc oxide grow in, wherein the zinc oxide film now becomes a thin film. Now let us look at this zinc oxide film which we have deposited on the substrate surface. As you see, what I have drawn is just like if you have a hot kettle and water is evaporating and you put your hand on top of the kettle, you will see water drops collecting on your hand. Only when sufficient water drops have been deposited do they coalesce to give you a smooth film on your hand. Similarly over here, the zinc acetate has gone through this hot zone, out through the hot zone, wherein the zinc acetate has decomposed to give you zinc oxide plus carbon dioxide plus water, and the zinc oxide droplets have gone and collected on top of this substrate surface. Is this a dense material? The answer is no. It is simply because that the potential energy of the zinc oxide grains which were generated by calcining zinc acetate did not have sufficient energy to move around. So, if I want a zinc oxide film, so let us say for any sensing application, nobody would buy this granular porous zinc oxide film because it would peel off, like say the old paints in your houses. they peel off. So, here this structure I have drawn is useless for the purposes I have mentioned. So, how do you densify it? So, I have to redraw the graph all over again, it has got too cluttered. So, now I am having redrawn it, that is I am back to where I was. I have a nebulizer which is giving off an ultra fine spray. It goes to this hot zone where the zinc acetate decomposes to give you zinc oxide, carbon dioxide and water. The zinc oxide deposits on top of this. Now, in this last diagram which I had used over here, I had said the word just substrate. But if I now make it a heated substrate, that is behind the substrate, right itself, there is a radiant heater. Of course, the substrate is rotated. This is a radiant heater behind the substrate. So, now I have got a heated substrate. I am using the nebulizer to spray zinc acetate through this tube into a hot zone, and after it passes to the hot zone, it is purely zinc oxide. Now, all of you know that zinc oxide loses oxygen when heated. That is, zinc oxide it loses oxygen. The lattice expands. So, right now what I am saying is, with the radiant heater over there, what is it that we gain? Here, when there was no radiant heater, the zinc oxide vapors had gone stuck on the substrate surface and then covered the surface totally just by physical contact. But electronic materials do not forgive. If they want a dense material, they shall have it dense. So, when I am using this radiant heater, as the first zinc oxides are being deposited, and what happens is, as these particles are depositing, they are also what I call delta heat sintering. So as I heat it, what will happen? It will become something like this. Something which is called sintering where the grains are joining. So right now you can imagine that in a heated substrate growth of solution sprayed tin dioxide, what we have are large grains. It means these are dense grains. So, and by varying the deposition condition, varying the deposition means control spray rate. Because if the spray rate is too high, even if the substrate is heated, too much materials will fall on the substrate and they will itself start evaporating, causing lowering of temperature. And as a result, we will not get the dense sintered substrate. In case you want to have zinc oxide, tin dioxide, what do? This is a dopant. In that case, what I would take is zinc acetate, SnO2 it has to be, and another tin salt, even tin acetate is available. I said doping. So let me talk of dopant levels. So here I will take the zinc acetate, the tin acetate, or even the tin nitrate solution in desired ratio, mix it and spray it. Now here, using this process for single component, it's a routine process now industrially for making zinc oxide thin films. Zinc oxide thin films are used as phosphors, as chemical sensors. The Japanese today, or they came out with it about 5 years back, a knife for cutting fish and also understanding, has it rotted, is it stale. So there they have a coating of zinc oxide tin dioxide, they have got lots of coatings, which the basic fundamental principle of the knife is a fresh fish has a particular surface tone. That is, if I want to cut myself even with a blade, I will feel a distinct type of pressure on the blade which will not be there if I try to use it to cut a cadaver, means a person who has died, because the muscles are already dead. So that knife, as you cut through, it measures the pressure, the force required to cut the fish. Secondly, it measures if it has indeed rotted, has methane been emitted. This is the first crux of the thing that the knife can do. And they are all made with zinc oxide based thin film with different dopants, because zinc oxide thin film is best for determining whatever they want, whether it is freshness, whether it is, the material is emanating carbon dioxide, all of that using zinc oxide based film. So, here it is obvious that when it is a commercial product, the technology has been developed for making single 2-component thin films by solution spraying. The technology has today developed to that level where the modelings told us what to give it, what to do. And in the act, what are the factors for having a 2-component dense sintered film? One is, as I said, the spray rate. Second, the temperature. The way the temperature is fixed is not arbitrary. The way the temperature is fixed is after a rigorous experimentation, which is called TGA or DTA. This is thermogravimetric. This is differential thermal analysis. They are done the same experiment. Let me talk of what they are, because a ceramist needs to know this, and of course you will have to handle it during your characterization part. We have a tube which is fused alumina or stabilized zirconia. Stabilized zirconia. This tube has furnace heating coils around it so that it can be heated to around 1400 degrees centigrade. There is a support wire hanging in, which is platinum, which has 2 crucibles at 2 ends. Further, there is a thermocouple beneath these 2 crucibles. This crucible is filled with reference material like, say, alumina, something that does not change with temperature. This one is the test sample. So, here I have got alumina which does not undergo any chemical change, and here is a test sample. What is test sample? Is, say, zinc acetate, which when heated under oxygen will give you zinc oxide, carbon dioxide and water. When this happens, what will happen? The weight of this test sample will decrease, because the acetic acid has burnt off as carbon dioxide and water. So, the amount of weight of zinc oxide will be lower than that of zinc acetate. This is thermogravimetric analysis, TGA. By varying the temperature of this furnace continuously, let us say this is the T, say this is the temperature scale and this is the weight. Let us say the weight is initially 20 milligrams. So, we heat it around 100 degrees centigrade, around 80 degrees it starts losing water, then the chemisorbed water, this is the physisorbed, and this is the chemisorbed water. Then the actual decomposition occurs, zinc acetate to zinc oxide. So the weight drops and at a particular temperature it becomes constant. This is TGA. Now, what does this tell us? When I am going to deposit zinc oxide over here, by spraying a zinc acetate, I want to know what will be the temperature, what should be the preferable temperature of the coil. So this TGA has told me that the temperature should be somewhere over here, because at this temperature all the zinc acetate has decomposed, giving me a zinc oxide. Now, most of us ceramists use a double fail technique. Is when this is happening, what is happening? Is it liberating heat or absorbing heat? So this will absorb heat, and in that case, look here, I have got the two crucibles maintained on an insulating stand with two thermocouples in it. I have said alumina does not undergo any chemical change, but this test sample does, as I have told of zinc acetate over here. So during this run, say I am going again along this temperature, say room temperature to say 900 degrees centigrade in air. Let us say I have gone from room temperature to 900 degrees centigrade in air. What I intend to do is, I intend to measure the del T between this. The whole idea is, let us say I am at 100 degrees centigrade. At 100, both of them will be at 100 degree. Oh, will they? Or I said physisorbed water goes out. When it goes out, some heat will be taken away. So if I look at the temperature del T, the difference in temperature between the reference and the test sample, it shall be a finite amount, a small amount, because the physisorbed water is going away. As I go more towards this temperature, the chemisorbed water will go away. So the del T will increase by little larger amount. So if I took, because this whole thing is cluttered, this T, this is 0, this is 900 degrees centigrade, and this is where TGA said decomposition is complete, and I measure the del T. This is 0. So fine, what will happen as it comes when the water is lost, I will get this. As the chemisorbed water is lost, I will get another blip, because the heat will be taken away. And finally over here, I will see a large blip where this reaction is complete, because it has decomposed, it has taken away heat, it does not liberate heat. So this is the temperature at which zinc acetate decomposes, and I have verified it from two techniques. This is TGA and this is differential thermal analysis. So this particular temperature is the rough range around which this temperature will be kept fixed. Now, what will be the temperature over here? As I had told you earlier, the zinc vapors which come off these nebulizers dissociate to give you the zinc oxide. But is that merely so? Unfortunately, no. Unfortunately, no. Let me take a temperature gradient. The temperature is rising in this direction. Let me care to bother to put certain numbers. This is room temperature. Let me label this 100 degree. This is 400 degrees centigrade. (700 degrees centigrade), 1000 degrees centigrade. Let's say I've got a tube where the temperature varies in this fashion. Now I have a single droplet of the zinc acetate solution. What will happen as it moves through? As it moves through this zone, it will lose water because it's a solution. It's a droplet which has got zinc acetate. So as it moves through here, it becomes smaller. As it goes over here, it becomes still smaller. Now, depending on the original concentration of zinc acetate in solution, what may be happening over here, if I now magnify this, if now, if this droplet size and this one are the same, I may have a saturated zinc acetate solution over here. And as this moves in still more, say 600 degrees centigrade, the situation may be over here that this is the droplet and within it zinc acetate crystals have separated out. This is an entirely plausible situation. Entirely plausible situation. That is, here it was supersaturated and here zinc acetate has separated out. Is that a good thing or a bad thing? Let's explore. Zinc acetate will, let's say, has decomposes entirely over here at 700. What would happen? This would break up to give me ultrafine zinc oxide powders. So this zinc acetate, once it has crossed 700 degrees centigrade, which is its dissociation point, would give me ultrafine zinc oxide powders. Now these powders can be really engineered very well by controlling the flow rate, the rate at which this is going up, the temperature and the concentration, so that on the substrate surface you have 30 nm to 50 nm size powders. Now, you have a radiant heater. Remember, I talked of using a radiant heater over here so that I could have dense film. Now, if the radiant heater is there, then what happens? These particles, when they reach the substrate, they have just gone and stuck over there. Now, with the radiant heater, they move around, spread, they sinter, and they can give you a very, very, very dense film of zinc oxide, which is, I have grown very smooth, 100 nm thick, 2 nm RMS roughness films using this method. It requires patience, but this is one of the most simplest techniques of growing thin films. Now, even as I said, I want to dope it, or I want, say, a 50-50 mixture. Fine, I take zinc acetate, the other thing is tin dioxide, so take tin acetate or tin nitrate, mix them and spray them. If their dissociation temperatures are the same, they will co-deposit and you will get a solution. You will not get separate zinc oxide, tin oxides, but this is something else that I shall handle in my next lecture. This is a big field, it will require time. Thank you.